All righty, friends. Hello. It's good to see you all again. All right. So we're going to just keep continuing through calculus here as we get to some more of the logarithmic functions in general. And in calculus, there's one function that we really, really like a lot, and that's this one, the natural log function. So if you guys don't remember, the natural log function, this is basically the log of base e. Now you can plug in your calculator to see what E is, but it's called the Euler number. It's 2.718 2834 and dot dot dot. All right. It's named after Leonard Euler. I think Leonard Euler is just one of the coolest mathematicians of all time. So majority of his life he was blind, right? And so he was able to, and even still, and we know him for a bunch of things, but one of my favorite things about him is he was able to prove that the 5 fundamental numbers in math actually all relate to each other, which I just think that's kind of the coolest thing in the world. You guys don't know enough yet to be able to do this proof or do it in general, but when you guys learn Taylor polynomial in Calc 2 or Calc BC if you're a junior, you'll figure out how that whole thing plays out in general, but it's a pretty cool proof, man. So anyways, so E, when I was getting my master's, I had to do that proof for a whole bunch of math people. So I had to stand up, do a little seminar on it. So it's one of my favorites. So E comes from this general limit right here. When you take it all the way out here, this is where we see this value of E pop out. Now, we have the 5 fundamental numbers. A lot of math people think there's probably more. Some don't. I think there's probably a bunch that we just don't know about. I'm not going to argue left and right. If somebody tells me there's not, okay. But we do have these 5 that we know for sure. So anyways, just a quick little review before we start diving into these. We do need to remember a couple little rules of logs. So if we have a log, just remember that log is an inverse of an exponential function. So if I wanted to, I could change the form from a log into an exponential function at any time. So in terms of a natural log, if that base is E, even though we don't see E, that base is E, it'd be the same thing as like E to the Y equals X. So we have these different rules that pop up. And we also have some values that we've learned along the way. Anytime you take the log of 1, that always equals 0. Likewise, if you take the natural log of 1, still 0. Doesn't matter if that it's natural log or not. And the other one, that value that we need to be able to recognize right away is if you have a base of your log and it equals the number, well, that equals 1. So that means for us, the natural log of E would be equal to 1. And then we have our 3 log properties. I don't remember if you guys, you guys use these in integrated 3 and in pre-cal, so you guys should be pretty familiar with them. So if we have an exponent, we said the exponent always goes to the front, and not in the back. The back. All right, so we just bring that in up to the front of it. If I have 2 logs that I'm adding and they have the same base, so if I'm adding 2 logs and they have the same base, I can rewrite that as 1 log and I can multiply. Or I could go the other way. If I'm multiplying 2 things, I can expand it and write it as 2 separate logs. And likewise, if we add them, that can be multiplying the terms, where if we subtract them, that would be the same thing as subtracting the terms. So we have all our little log rules. Those haven't gone away. We're still going to be using them. So And before we get into them here, we're just going to do a little bit of review on just some log things in general. So for instance, what I want you guys to do, if you don't mind, if you do mind, it doesn't matter, still want you to do it. I'd like you to expand and condense. Go back to our pre-cal days, go back to our integrated 3 days. I'd like you guys to expand this log right here. So 3y times the square root of x plus 1 all over x plus 3 to the 5th and y minus 1 squared. So we're going to expand that. And I want you to condense this one. So expand means to write it as every term with its own log. Condense means to write it as one log, just in case you happen to forget the terminology from back in Algebra 2 pre-cal days or Integrated 3 pre-cal days, depending on where you came from. 1/3 natural log of x plus 4. Minus natural log of x plus 7. And plus 7 times the natural log of x plus 1. All right, friends, I want you guys to go ahead and pause the video for a second and expand and condense as needed. All right, let's see how I did. First up, anytime we have things that are in the numerator or being multiplied, we said those are essentially going to be separated into addition. So natural log of 3 plus natural log of y plus the natural log of, and I'm going to go and change that square root of x to an exponent. And anything in the denominator is going to be a subtraction. So we separate everything out. And then anything that has an exponent left over, we bring it to the front. So that means the 1/2 is going to come out in front. Up to this point, when you guys have been asked to condense an integrated 3 algebra 2 or pre-cal, you've never done anything with expanding. Turns out in calculus, we like to expand logs. It makes our lives much, much, much easier. So this will be the year that we actually do want to expand. And we'll see some of that coming up here in a second. Well, condense is going the opposite way. So every positive log is going to go to the top, and every negative log is going to go to the bottom. But first, we got to get rid of the numbers in front. So that means the 1/3 is going to go back to being an exponent. And you guys did this a lot back in pre-cal and algebra 2 and integrated 3 because you wanted to solve trig equations. And in order to solve a trig equation, you needed to condense it so it was a single log. So then you could go ahead and solve it. All right, all the positive logs go to the top, all the negative logs go to the bottom. So x plus 3 to the top. X plus 4 to the 1/3 on the bottom. X minus 7 also will go to or x plus 7 will also go to the bottom. And x plus 1 to the 7th, that'll go to the top. And friends, we're just about done here, except for one problem. I have that 1/3 still, so that means I need to go ahead and do a cube root here real quick. So I have x plus 3, x plus 1 to the 7th. all over the cube root of x plus 4 times, oh, what was that, x plus 7? And there we go. All right, so just a real quick review on how the log rules play out, because we're going to need to know those today for some of the things we're going to be playing with here. So I'm not going to go through and prove this for you on the video. I know some of you guys like the proofs, so if you go to 5.1 on the printed notes, I have gone through and proved both the derivative of natural log and eventually e to the x when we get to e to the x. So you guys have those available to you for my friends that really like proofs and want to see how the whole thing plays out. But for the rest of my friends, turns out the derivative of a natural log is equal to 1 over x. And it kind of makes sense when we look at derivatives. Before, we couldn't do a derivative if it was x to the negative 1, because when you do your power rule for it, or integral that is, I'm sorry, when you did your power rule for it, you'd have x to the 0 over 0. Well, that doesn't work out. Well, it turns out it was never meant to work out. Well, again, we'll see this tomorrow, so don't worry about it right now. But anyways, the reason it didn't work out was because it wasn't a power rule, it was a natural log. And some natural log integrals look a lot like power rules. Sometimes it's hard to tell the difference. Good news is derivatives, not hard to tell the difference at all, because you're just told to find the derivative. So we'll go ahead and start here. I'm going to throw up some derivatives here for you. We're just going to find the derivative of some various functions here. So I'm going to do the first one here, and then I'm going to give you guys a few so you guys can try to see how you would go about doing a derivative. So natural log of x minus 3. So whatever's in the parentheses, that's my f of x. That will always go to the denominator. So that means when I do my derivative, my x minus 3 will go to the denominator of my fraction. And whatever the derivative is of that, whatever's in parentheses, that'll go on the top. So the derivative of x minus 3 is just 1, so it's 1 over x minus 3. That's all we're doing with these here, friends. We're not going to be doing a whole heck of a lot. So let's have you guys try a couple of these to see how you guys do. So f of x equals the natural log of x cubed. Let's do g of x is, the natural log of, let's put some stuff together, x plus 5 to the 8th power. This is where in my mind, I'm hearing you guys saying, all right, Williams, why is it you do the easy ones and we do the hard ones? Oh, because it's funny. And 3x minus 7. And h of x equals the natural log of, we don't want to leave the trig out. Let's put a sign up here. Sine of x all over, let's really make this fun, 4x cubed minus 8x squared plus x minus 1. Now, before I have you guys pause video to solve this, here's my little hint for y'all. Expand them. Expand your logs and separate them. All right, go ahead and pause the video, see what you can do. All right, so expand them. Well, in this case, if I wanted to expand it, all I have is this 3, but I can put that in front, so I have 3 times the natural log of x. So that means my derivative is 3 times 1 over x, which is the same thing as 3 over x. Now, friends, I don't have to expand it. I could have done it the other way. I could have just said, all right, well, let's put the x cubed down in the bottom. It's still going to be the same thing. And if I put x cubed down the bottom, the derivative of x cubed is 3x squared. And some of you might look at this and say, well, I actually prefer doing it that way. Well, that's all said and good, and I have no problem with that. But when you start looking at g of x and h of x, when you have product rules and chain rules and quotient rules mixed in, you definitely don't want to deal with that. It helps to expand it. So I asked you guys to expand it. So if I were to have expanded this one, I would have first done natural log of x plus 5 to the 8th plus the natural log of 3x minus 7. And I'm combining it with plus because it was multiplication in between. 3x minus 7 to the 1/2 power. And now notice, I have these 1/2 and 8, they're exponents, so I'm going to move my exponents to the front. So now I'm going to have natural logs that are pretty straightforward. They're not going to be all that bad. So I got 1/2 here, natural log of 3x minus 7. Now, once it's all the way expanded, now it makes the derivative so much easier. So I have 8 times 1 over x plus 5 plus 1/2 times 3 over 3x minus 7. And friends, again, if it's on the FRQ portion of the AP test, leave it alone. Don't simplify it. It's on the multiple choice. Well, we would need to simplify that a little bit. So let's go ahead and simplify just a little bit. And I end up with 8 over x plus 5 plus 3 over 6x minus 14. All righty. That's what I mean by expand. So if you didn't get a chance to expand this last one, why don't you go ahead and do that and see if you can deal with this derivative yourself. All right, so if I'm expanding it, I see something in the numerator, so that's going to be a positive natural log. And something in the denominator, so that'd be a negative natural log. If you notice here, all of a sudden, this ugly thing that was going to be a quotient rule and all kinds of just bad stuff ends up not being, honestly, all that bad if we expand it. So sine goes in the denominator. And derivative of sine is cosine. Cosine goes in the numerator. Minus 4x cubed minus 8x squared plus x minus 1 all over, what's that going to be, friends? 12x squared minus 16x plus 1. And you can leave the answer like that. One thing I do want you to notice here is it's cosine over sine. That looks like cotangent to me. So if this was on a multiple choice, don't be surprised if that answer got changed to a cotangent. So in other words, the derivative of natural log of sine x actually equals cotangent. Huh. That's kind of interesting. I guess we'll probably see something to do with that tomorrow when we look at integrals of natural logs. All righty. We're kind of going through here a little bit. Had a chance to work on some derivatives. Let's kind of do some applications here. Let's let f of x let's let f of x be equal to 4 times the natural log, oopsies, 4 times the natural log of x minus 3 plus 2x minus x squared. I want you to figure out, first of all, what is f prime of 4? I want to know the tangent line. So the equation of the tangent line. Add x equals 4. And then I want you to use that tangent line to approximate f of 4.1. Let's try this. All right, let's pause the video, see what you can do with that. All right, well, first up, we've got a derivative here. So if I take my derivative here, I have 4 times 1 over x minus 3 plus 2x, so that'd be 2, minus 2x. So if I plug in 4 into that, I get 4 times 1 plus 2 minus 2 times 4, which would be 8. And that would be equal to a whopping 426 minus 8, negative 2. So if I'm going to do part B where it says find the equation of the tangent line, I already know what the slope is now. It's negative 2. What I don't know is what was the original value. So 4 times the natural log of 4 minus 3. Well, 4 minus 3 is 1. The natural log of 1 is 0. So that's not too bad, actually. So f of 4, I end up with 0 plus 8 minus 16. So f of 4 is negative 8. I almost said negative 16. That would have been bad. So our tangent line is y minus a negative 8, so y plus 8, equals negative 2 x minus 4. And let's see here. Last and certainly not least, friends, if I want to do a linear approximation of it, so that means I got to take my tangent line real quickly and move it over. So that means f of 4.1 is approximately negative 2 times 4.1 minus 4 minus 8, which is negative 8.2. There we go. All right, all right. Let's keep going here. Let's see some other things we can possibly play with here. Let's try this one. Evaluate dy dx at, oh, what point should I give you? Let's go 1, 2. For, I better give you an equation here. Which one am I thinking here? Let's go x plus y squared equals natural log of y minus x plus 5. All right, why don't you pause the video and give that one a whirl, see what you can do with it. All righty, friends. So I'm dealing with a derivative here. So derivative of x is 1. It's a nice implicit derivative here. So 2y times dy dx equals y minus x goes in the denominator. Derivative of y is 1 dy dx minus 1. And then the derivative of 5 is 0. But since it's 0, I'm going to go ahead and get rid of it. Well, no, this doesn't look like too much fun. So how about just for a quick idea here, how about I put this over 1 real quick? Because I'm going to cross multiply this and see if I can't try to get everything out here. So I get dy dx minus 1. Y times 1 is y. Y times 2y is 2y squared. Let's see here. Don't forget the dy dx at the end of that one. Negative x times 1 would be negative x. Negative x times 2y would be a negative 2xy dy dx. All right, so I need all the dy dx's on one side here, so we'll leave this dy dx over here. Now we'll get a minus 2y squared dy dx there. Whew. I'll be honest, friends, from what I saw you guys' work on implicit derivatives, you're pretty good at it. I mean, other than you guys kind of sometimes get messed up with the product rule, x and y are together. But the issue that kind of gets us a little bit is when we have to deal with the algebra. You guys are not big fans of the algebra. Alrighty. So if I factor out my dy dx, I get 1 minus 2y squared plus 2xy all over 1 plus y minus x. And if we get the dy dx by itself, we end up with something looking kind of similar to this. 1 plus y minus x, 1 minus 2y squared plus 2xy. All right, now friends, we just got to evaluate this here real quickly, like whoop. Equals, so that's at 0.12. So we're going to plug all that in here. So 1 plus my y value was 2. And let's see here, minus my x value is 1. All over 1 minus 2 times y squared plus 2 times x times y. So we're going to plug in our x's and our y's. Let's add x right here. And let's see, I add some y's here. All right, what do we get there? We get 2 all over 1 minus 8 plus 4, which is negative. And again, I wouldn't have simplified this at all if it was on the pre-response portion of the test, but multiple choice, I'd have to go ahead and be able to do that. All right, let's try one more application here just for the fun of it, and then we'll go ahead and call it a day. Determine any relative extrema for f of x equals the natural log of x squared plus 1. All righty, friends. So we're going to go ahead and remember, a little three-step process. We're going to say what we're going to do. We're going to do the work, and when we're done, we're going to say what we found. Oh, my daughter got me a Starbucks. Oh, so kind of you. All right, I want you guys to go and pause the video and give this one a shot. All righty, let's do it. All right, so friends, we're going to say what we're going to do. So relative extrema can exist when f prime of x equals 0 or when f prime of x is undefined. So remember, we give ourselves permission now to go ahead and do all the things we need to do. So f prime of x equals x squared plus 1. And remember, we have to do the derivative before we set it equal to 0. Now I can set it equal to 0. You can't do it too early, gotta wait. All right, and when I solve it here, I find out that x equals 0. So what I need to know now is there a relative extrema at that one critical number? So x equals 0. I'm going to do a first derivative test. Got to test my values here. So let's plug in -1 in. See what that does for us. And let's plug in +1 in here. See what that does for us. And if I plug in f prime of -1, I'm going to end up getting, friends, a -1. So that means f prime of x is less than 0. And if I plug in 1 in, I get a +1, so it goes to greater than 0. So it turns out if it goes from less than 0 to greater than 0, it means I have a relative min. So we're going to plug it in now to figure out what is the value that goes with it for the y value. So f of 0 equals natural log of 0 squared plus 1. So the natural log of 1, which would be 0. So that relative min is going to be located at the point 0, 0. So we said what we're going to do. We did the work. Now that we're done, we're going to say what we found. And then, friends, we can call it a night. F of x has a relative minimum at 0, 0 because f prime of x changes from f prime of x less than 0 to f prime of x greater than 0 at x equals 0. All righty, friends. Well, that kind of takes us to the end of the day. So go ahead, and I'll see you guys in tomorrow. We'll talk a little more about this. Take care.